All right. This is now we're into the home stretch. We're into the second week of improve, and that's it. There's only 2 weeks of it, and then next week we'll take a break for Good Friday, and we'll pick up with the control phase, which is also 2 weeks. It's not 3. So, and then we'll get into the review the following week for the finals take home. It's a no stress final. And hopefully, you can start to think about what you want to do we can start to plan the presentations for the final too, where you take my weight data. I think I have Warren is thinking about, he's looking at sound noise levels in Oxford, and he's got a lot of data, and he might use that. So even though I recommend, I give you my weight data, you don't have to use that. You could use something that you might like, something that you might be working on. But the idea of the presentation is just to use 4 or 5 of the tools, probably 4 or 5, I think would be the right number, in practice and present to us, to the group, okay? So without further ceremony or ado, I'll switch it over to, I'm going to start again with the math practice because I think that's been working a lot better. Instead of just getting into the PowerPoint, where the PowerPoint, I think the objective is to confuse and paralyze people. I think the math practice, it just helps us to make sense of some of this stuff. So I'm going to start with right here on the homework that was assigned last week. And the purpose of the homework is, I like you to, use the tools, and I think if you follow watch the video, the recording, the homework should be fairly easy. So last week, my favorite tool of all is correlation, right? And because it allows us, as we're in the improve phase, to begin to predict. And if our predictions come true, then we know that our process is in control. So in this case, the homework was, is there a correlation between my weight and my pulse rate? And what I asked for you to try was to look at it 3 ways, right? We know if I just use the equals correlation, you see that the formula up here in top left, and I highlight the cells, I get a value of 0.375. And what does that number mean to you? When I see a correlation of 0.375, what does that tell you?
Weak.
Right, a weak positive correlation, right, between my pulse and my weight. And then the next part of the homework was, all right, let's see what that looks like with an XY diagram. So again, this is pretty simple too, in that all I have to do is highlight those 2, pulse and weight, and then go to insert and recommended chart, and I get this Milky Way. And again, I think it kind of proves out with my R value of 0.375. And I think we could all agree that looks like either weak positive correlation or none, right? Like, in other words, it doesn't matter what my pulse is, my weight, but there is, in fact, a weak positive correlation here. And you can kind of see that things are trending north, right? North, that'd be what, northeast a little bit. All right, but very weak. And then the third part of the homework was, just practice using your data pack, to get the exact same number. So now there's 3 ways of doing the exact same thing. So today, what I wanted to talk about really is 3 main concepts. One is what we mean by regression analysis, residual analysis, and then the last 15, 20 minutes is going to be just a review for some of you guys in terms of lean concepts and how we use them in the improve phase. So let's start with regression. It was really easy when I'm going to go back to this work here, the correlation. You remember this stuff? This was age and salary, and this is kind of how I taught you guys correlation. Is there a correlation between age and salary? And just really quickly, I'm going to go ahead and just draw my XY diagram again. And to do that, I just highlight my data. and then hit insert. And I go to recommended charts. And that's what I wanted right there. That's the one I want, the scatter chart. And it pops it right on there. And again, why is this in the improve phase? I've collected a whole bunch of data in the measure phase. Probably this is only 10 pieces of data, but I might have 500 of them, right? Or in the case of my weight, I might have 720 of them. And I want to start to understand, is there a correlation, not causation, between a person's age and these 10 subjects that we tested here? There was a strong positive correlation, almost perfect, right? If you look at the R value, it's at 0.9922853. So all regression analysis is, it's a way, it tells us how predictable is our process. And basically it's about, how do I draw a trend line through this data, a line, right? So like the two things we want from our processes is, one, are they stable, right? Or are they all over the place? Are they in control? And then secondly, are they predictable? So to draw a trend line, all it means is, if I throw another age in here, like say I threw an age 30, where based on the fact that there's a correlation between age and salary, what salary could I expect at age 30 with these 10 subjects? So the way that's done, I think I'll do it graphically first, and I'll show you a bunch of other ways. But all I do is I highlight my data, and I right click it, and it says add trend line. And you can see, could you guys see the small dotted line there? Add trend line. And then I'm going to go ahead and do two other things. Down here, when this box pops up, and this is going to be the homework, for that Milky Way, that blob, we're going to display the equation on the chart. So I'm going to click that, and you can see that an equation just popped up. And I'm going to display R squared value on the chart. Everybody see that? And I'm going to probably just paint this thing yellow, the line, just so you can see it easier with, with the blue. So I'm going to go to make it yellow, and I'm going to make it a solid line. And maybe I'll make it a little thicker so you can see it easily. And I'm also going to blow the formula up a little bit so you can see it. Oop. Put it over here. And I'm going to take you through the formula real quick. All right. So that is the formula. Y is equal to 1320.5 minus 6,627.7. So if I plug a Y in here, and the Y's are, again, my salary, the dependent variable. If I take this number 1320.5 and multiply it by that X, that's the formula to get the next Y. Like if I said, hey, look, my X is now 30 years old. So I'd take the age 30, multiply it times 1320 minus 6,627, and I would get a salary, all right, that I could expect based on this set of data. So it's a way of predicting. So let me tell you what these variables are, the 1320 and the 66.27. Well, the first thing, the 1320, let's look at a couple of Excel formulas. One is going to be equals the slope. Oops, slope. And the slope of that yellow line, all it means is it's a number that represents the rise, like how far north it goes up, and the run, rise over run. So it's a coefficient of, for every 1 unit up, how far do I go over, right? So that's the slope of the line. And to get that, using the, I know what I'm going to get, right? I'm going to get that 1320.5, right? But I just want to show you how to do it with these, the Excel formula. So it says it's asking me for the known Y's. So I'm just going to highlight those. And then it tells me to put a comma in. And then it's asking me for the known X's. And I hit that. I hit enter. and I get 1320, which is right here. I just got that formula, right? Just by doing it, by making the graph, right? And clicking on add formula. I just want you to know where that 1320.5 came from. And then the other thing I need to know, the only thing I need to know now to draw this trend line, which is regression analysis, is where this line is going to intercept my y-axis, which is my salary axis. Like, where is it going to cross? Like, once I have those two pieces of data, those two things, my slope and my y-intercept, now I can draw a trend line. And now if my process is stable, I can start to predict, right? So let's do the, I could also do the y-intercept using the equals, a function of Excel, and that is intercept, and double click that. My known y's, which is the salary, comma, and my known x's. And what should I get for an answer?
Minus 6627.7.
Hey, you get the A for the day, Warren. All right, so let's try. Like, I don't know if anybody has their phone handy, but basically, if I take a y that I don't know, I want to know what my salary is going to be at age, say, pick one that's not here, say 50. I don't see 50 on here, right? If I do that formula, 1320.5 times 50, and I subtract 6627.7, I'm going to get a salary, that I could expect based on the data I have. So it allows me to predict. I think about like how this would be useful in some of the processes that you have, once it becomes stable, and being able to predict. If I change this, if I improve this part of the process, then I know I'm going to get this result. Very, very powerful tool, I think. Any questions? That's regression analysis. So the homework will be to go back to the descriptive statistics. Let me grab it real quick. And go ahead and do the same thing, trend line through that Milky Way, because I don't know where I would draw the line, right, without the formula. So let Excel will do that for you, right? I just highlight that data and add trend line and add the formula to it and add the R squared. Well, I want to go back to the R squared for a second. The reason we use R squared instead of just R, remember the R value from last time was 0.9922853. The reason we use R squared instead of R is because sometimes when I do this formula, it's a negative number, right? It might be a strong negative correlation because you point in the other direction. So we often use R squared instead of R, just because when I square something, I'm going to get a positive number. That's the only reason. Any questions? We good on this one? Very powerful.
Bill, just to clarify, just make sure I understand. So the R squared, if you had a negative correlation, then that just gives you a positive result. Correct?
Exactly, because we're going to use that R squared number as when we get into the PowerPoint, as we get into residuals and other things. We need to have a positive number there.
Okay, gotcha.
That's the only reason.
All right, thanks.
Yep. And I think like if you figure out, if you square this 0.9928, I think it comes out to 0.98 something or 0.97 something. But that's a number we use for other formulas, because you really can't use a negative number in a lot of the formulas that we're going to use, that you would use later on. So that's all regression analysis is. When you think regression analysis, think trend line. And the why, the value of the trend line is, can I predict, if I don't have a piece of data, can I predict where it's going to be based on my process? All right. So having said that, let's go back to descriptive statistics real quick. Based on what you see here, can you predict, if I give you a weight, can you predict what my pulse is going to be?
Not very accurately.
Correct. And so knowing that, you know what I mean? So think about it as you get into the improved phase of on a process. You know, if I have a strong correlation, that means that I can go ahead and make that improvement, knowing that I'm going to get that result. And then we're just going to touch on multiple linear regression. This is simple, you know, single linear regression, because it's only pulse and weight, just two variables. Multiple linear regression would be my blood pressure, my pulse, my weight, and looking at how they correlate. All right. And we're not going to cover that too much, right? We're going to cover it in the PowerPoint, but I'm not going to, there's no homework on that. One other thing I wanted to ask you guys is going back to the beginning and understanding the value of process control and having processes that are 6 Sigma, right? That's just going to say on your certificate. So in the case of my weight, the 6 Sigma, all it means is there's a mean here that is the top of this mountain, right? And what's that? That mean is 184 pounds.
Yeah. Hey, Bill, sorry about that. You cut out there. Could you go back and repeat what you said?
Okay. How about now? Am I good?
Yeah, we're good.
Okay. Yeah. So again, the whole purpose of this is what I want to kind of get to is after 720 pieces of data, my health data, the process of my health, is it 6 Sigma? Is it within 6 Sigma guidelines? Is it a 6 Sigma process, right? And I wanted to kind of explain that. If I look at this bell curve, really nice bell-shaped curve, right, for these 720 pieces of data, and where's the mean at on this curve? Where's the average?
185.
Yeah, 185. So it's actually 184.59, right? So 185. See it right there. So all 6 Sigma means is there are less than 3 standard deviations away from that mean, right? So what we're talking about is because 6 Sigma is 6 standard deviations. So 3 would be on the heavy side, 3 would be on the lighter side. Maybe if you do this curve after 2 years, you might have had a much bigger spread of the data, but hopefully, you know, over the years, the process has become more in control by changing the inputs, you know, what I'm eating, sleeping, exercising, they're becoming more. And if you look at, so you take that 185 and 3 standard deviations heavy would be 12 pounds, right? Because each standard deviation is 4.25 pounds. So 185 plus 12 would be 197. And you can see that we're still under that curve, right? So I can conclude in the same thing the other way. 185 minus 12 pounds, you know, would be 173 pounds. You know, so we're very close to a 6 Sigma process here. It doesn't mean I can't drop dead raking leaves, you know, but all it's saying is the process is, you know, is in control. Does everybody make sense? Mm-hmm. How this all comes together? Mm-hmm. And the goal is all of our processes, we want them to have that small amount of variation. Okay. And when we have processes that are not in control, this is how we approach them. So I'm going to stop. If anybody has any other questions, the homework, everybody clear? Good. If you're missing homework, just, you know, please get it to me because it's important that I know that, you know, you at least try, practice. I think pretty much everybody's up to speed. If you have any questions or problems with it, let me know. All right, so that's regression analysis. Now let's get into the mind-numbing PowerPoint. And we'll start with the, you know, the improve, just where we've been. It's about redesigning the process to achieve improved capability. Improvements stem from an increased focus on root cause in the application of various lean tools. And you guys saw my blog this week about PTA Oxford. I don't know if you guys had a chance to see it.
There you go. Hey, Bill.
Hey, Bill, you're locked up again for the last half minute or so.
Welcome back, Bill.
I'm so sorry.
Welcome back.
We were concerned about it.
I'm sorry. The the improve phase is basically we've defined the project, we've measured a lot, we've analyzed what we measure, and now it's about making improvements from an increased focus on root causes where we better understand the data after our analyze stage, and we can make some smart improvements using lean tools. All right. And last week we covered selecting improvements. We got into just fishbone and a little bit of 5Y with my back and why it bothers me once in a while, which it really doesn't, just kidding. And then we got into my favorite tool of all, correlation, and then the XY plot, plotting a graph. And today we'll do the rest: regression, residuals, multiple linear regression, Boxcock transformations, and lean. So let me skip to regression, and we'll fly through this because we want to spend plenty of time with the lean. That's the fun part. Right. Here we go. So the correlation coefficient, that R, can't address the following questions. How much does one variable change when the other variable changes, right? It gives me a number, 0.9975 or 0.375, but it doesn't really tell me how one will change if I change the other. And that's kind of what we want to be able to do in improve phase. How can we set the value of one variable to obtain a targeted value? If my process is stable, I can begin to predict. If I change this, this is going to happen. And how can we use the relationship between two variables to make predictions? So that's where linear regression helps us, as you saw, with the rise over run and that equation. So simple linear regression means it's a statistical technique to fit a straight line through data points. And it's simple because we're only using one predictor. All right. When we get into multiple linear regression, that's two or more. And what the model does, we're modeling the quantitative relationship between the two variables. And there's a formula that that I showed you, how to, with the line and everything else. They just added a C on there, which we're going to get into in a second. But Y is the dependent variable. In this case, the salary. A is the slope, which is equals slope, and it tells us the rise over run. Then I can draw a line, or if I have that formula, I know if I punch in this X, I know what the rise over run is going to be, and I know what my y-intercept is going to be. X is an independent variable. B is the y-intercept, and then they added on here the residuals, which we're going to get into, and that's the difference between the actual y, what I expected, and the fitted y. Okay, the fitted y is what I expect because it's a data point that would land on the line. For example, at 50 years old, the formula is going to give me a salary. All right, that's the line salary. That's what would be on the line. It may or may not be that. It might be $5,000 or $1,000 either way of the line, right? But it's the error. It's a residual. That's what residual analysis is. The distance off the line that the data is. And we can use ANOVA, in looking at this kind of information. And if you remember what ANOVA is, we're looking at variation within data and between data. So we can take the things we learned in ANOVA, and I think there, the one we looked at was stress level within a shift and in between shifts. If you remember that one, but we can use ANOVA to kind of look even closer if we wanted to. And this is a kind of like a pretty good snapshot of what linear regression is, right? So my predicted value, based on what, that red line that goes straight, that's the line we're drawing, the trend line, the best fit line. That's our predicted value, for our data. And then we look at a couple of different things, in ANOVA, we look at vertical distance from not only the predicted value, but we also look at the vertical distance from whatever value I get and the mean, which is the green horizontal line. I mean, you don't really need to, I think I just like you to kind of understand, see this and understand, where this all comes from. And then we have total variations based on the mean. Okay. Now R squared, this goes to Mike's question. It's called the coefficient of determination. It's how much can I trust my ability to predict? That's all, right? The higher the number, the better the model, the better I can predict what's coming next, you know, given a certain X. And R2 ranges from 0 to 1 because we got rid of those negative numbers now, right? So there's no minuses anymore. And again, the last bullet point, higher the R2, the better the model that can fit the actual data. It means we've probably done a pretty good job of getting our process in control. And residuals, again, there's that same graph there. And a residual is that difference between my observed and what I thought it was going to be from that formula, the calculated, right? That trend.
There you go. Hey, Bill, we got you back. Sorry.
I can't hear you now. So you know what? Anything that you want to say, I don't otherwise I'll have to reboot again. I'm so sorry. I don't know what's going on with this thing. I can't hear you guys. I don't know. Maybe someone could put in the chat where I dropped off. Was it there? Was it here? Just give me a thumbs up, maybe. That's where I dropped off. Okay. I don't know what's happening. Maybe somebody hit a tree or something. Let me, all right, so again, residuals is basically the difference between my observed Y and what I calculated for the trend line. Like my trend line is my predictor, and the residual is nothing more than what the actual result was. So by using that formula for salary at 50 years old, there's a number that's going to come out, right? I put in 50 for my X. If I do that formula, I'm going to come out with a salary. It may not land on that red line. There's going to be some distance off of it. Okay. And that's what residual analysis is. It's just what's the average amount of difference off the line of my data points. And we want that to be just like we want our bell-shaped curve to be thin. Same thing, we want the residuals to be low. And that means we're getting more and more in control and more predictable. So the regression equation produces line of best fit. Differences between the predicted and observed are known as residuals, and residuals equal observed minus predicted. And it's just a way of knowing my ability to predict it. You know, I know my process is totally in control if I can predict using it. And the quality of linear regression models should be assessed by defining residuals and examining residual plots. And both the values of both the sum and mean are 0. Regression equations are generated on the basis of certain statistical assumptions. This is not on the exam. This is just for your, in case you want to store it somewhere. It helps to determine the validity of these assumptions. And again, all it's about, residuals and regression analysis, is our ability to predict. I'm gonna stop with that. And then obviously multiple linear regression, if they're just going to throw on another variable, you know, so it will be weight, blood, pulse rate, blood pressure, and there's a formula. So obviously more complicated, but very similar, in order to predict based on 3 or more pieces of data. I'm going to quickly go through this Box-Cox transformation. The idea behind Box-Cox, it was started in these two guys. One guy's name is Box and one guy's name is Cox, and they came up with this idea that if I have data that is not a bell-shaped curve, I can apply a formula to that data to make it look like a bell-shaped curve. That's all. Because think about like how nice it is. Once I have a stable process, all the tools that I can use in terms of predicting, in terms of, it's just such a nice, neat, you can do a lot with once I get my process in some form of a bell-shaped curve. But in cases of discrete data, I could use box-Cox transformation to turn discrete data, which is stuff that you would count, not measure, yes, no, good, bad, that kind of thing. I can actually transform that also. It's not easy. You must preserve the relative order of the data. It needs to be smooth and continuous. Usually you use Minitab to do it. Like, so it's just something I wanted to mention. It's not on the exam, but there are ways, if anybody ever comes across it, where you want to transform data so it behaves like a bell-shaped curve, the box-Cox is what you use. And the advantages are that linear regression is easier to do. And that's what we want to, that's why we like to use linear regression, right? But non-normal data can be changed to resemble it. And the disadvantages are it's difficult to understand transform units, because now we're not talking about salary dollars or pounds. We're talking about a coefficient of some kind. All right. And it's difficult without automation. So, and basically this is what it does. It can turn on the left here, a graph that looks like this into something that resembles a bell-shaped curve. And that's a chi-square on the left, by the way. All right. God, it's so frustrating. I can't hear you people. All right, so let's get into quick. This might be a review for some people, but the lean tools and practices, all part of the improve phase. For those of you guys that saw my blog this week, I blogged about the PTA Oxford's project on the assemblies. I think I mentioned Jim in there, and Kent, and a whole bunch of people, Greg, and your customer. But that project pretty much followed the DMAIC, right? The fine was, we're not looking at all of Cat 1, from the minute it gets molded to receiving the materials to mold it. All we focused on was the assembly. And the assembly was taken 3 or 4 days. So that was the summary of the define phase. And the measure phase was really the value stream map, because mapping fits nicely in that measure phase, because in the course of doing the map, we measured hundreds and hundreds of pieces of data, and it was all time-based. How long did someone have to hold on to a part? How long did someone have to wait for a part? A lot of quantifying the process in that measure phase. And that took probably out of the 4 months, maybe 2.5 of the months, is getting everybody up to speed in the measure phase. And then once we got done with that, then we got into the analyze phase, which was, all right, we have all this information. How do we make it where we know what to do next? And that was probably a few weeks too, and then we got into the improve phase, and that's kind of where we are now, where we're actually taking all that information, all that analyzing, and saying, all right, what are some smart improvements? And I think, in terms of going from 20 assemblies an hour to 35, even there was an hour where there was 40, there was a lot of these lean tools that got practiced, tried. And most of the suggestions came from the operators that actually do the assembling out on the floor. So I think this is a really good review of lean practices and where they fit into the DMAIC. They improve and obviously they fit in the improve phase. So just as I think if the one thing I'd like to impress upon on everyone, if you're as a lean company, as a lean practitioner, as a continuous improvement person, is just getting people to see these 8 things, the 8 ways, right? This is half the battle, is because a lot of times we do work and we don't think of it as wasteful, because it's work we always did. It's the way it's always been done. And, we don't mind going and walking extra 100 feet to get something. We don't mind waiting. It becomes part of the job. So the first hurdle is getting everybody to see these 8 ways. And you always remember, the easy way to remember is the acronym downtime, defects. And think about it. I like to think of the concept of flow, Lean is about creating flow, and flow is the order comes in and it never stops moving, and then it gets shipped. And these 8 wastes are things that stop the order from flowing. Like if I have defects, if I find a problem, I have to stop, you know, and I have to either rework it, I have to move it off the line, I have to put it back in inventory, I have to scrap it. The second one is overproduction, and that is basically making more than my customer needs. And my customer is the person I hand my work to. All right, so and that comes down to, and it's really overproduction it's known as the godfather of all the other waste, because it causes all the other ones. And that's what we saw a lot of with this assembly, right? We have a lot of inventory sitting in the cell in the beginning. We saw a lot of waiting because people were doing their task faster and passing it to the next step. And there might be, you know, a couple of units piled up waiting. It causes motion. It causes all the others. The third one, again, waste is waiting, and people wait, materials wait, a lot of waiting. Non-value added processing is doing redundant quality tests, for example, or quality checks. It might be sign-offs. It might be, these are all things that your customer will not pay for. So non-value added processing is an example of, we can't put on the invoice, this was checked 4 times. Your customer's gonna say, good for you, God bless. Or, you know, transportation, your part moved 1.2 miles. They don't care if it went 10 feet or 2 miles or 5 miles, doesn't matter, right? This is all called non-value added work. It comes out of your ability to pay, you know, to pay people, and your ability to give people bonuses, and it comes out of our profit. Inventory is sleeping money. It's money that we've already spent. We've spent it in payroll. We've spent it in materials. We've spent it in overhead, and yet we haven't been paid yet. And it takes the form of raw material, and it takes the form of finished goods.
Sleeping money
is basically how my hero Taichi Ono termed inventory. And then motion, obviously, is another big one. People moving about, people walking a lot. On the Cat 1 line, we have one particular area that we're really focused on the motion. You know, we're probably looking at putting a pedometer on the operator to see how many miles she walks in a day. That's all non-value added work. And then the last is, of course, treating people like robots, and I think we're way past that. This is probably, you know, more and more companies are understanding that the people that understand the work the best are the people that do it every day. They're the true process experts. And the only reason they don't tell us is because we don't ask them, or if we ask them, we don't really listen. So it's really about just listening and understanding. Those are the 8 wastes. Those are probably the most important part of the lean part of it all. And here's a few tools we're gonna go through quickly. There's a bunch of them. You could probably spend an hour on each one or more, a couple of weeks sometimes on some of them. But just to give you an overview, a flyover on some of these lean tools. 5S, you know, huge effort in Oxford. You know, every inch of the place is being broken into zones. There's audits going on every week. There's huddles going on every week. But this is basically the theory behind 5S. And sometimes you hear 6S because people will add safety. I'd say 50%, you know, they include safety in it. And half the people say 5S. And it's a systematic way to organize, order, clean, and standardize a workplace. And so it stays that way. This is probably one of the most difficult of all the lean tools, because you have to gain agreement with everybody that lives in the area. Right? And that includes first shift, second shift, third shift in some cases. And everybody always says, well, start with 5S. It is probably the most difficult of all the tools. And basically it's a process, right? So it's a circle. It keeps going forever. And it starts with sort, straighten, shine, standardize, sustain. And the way I like to describe it is, if I want to clean out, if I want to 5S my garage, for example, what the sort means is I'm going to take everything out of my garage, put it in the driveway, and figure out what doesn't belong in my garage, right? The things that don't belong going back in my garage, I'm either going to do a tag sale, Well, I won't do that. I don't want people at my house walking around. Or you might bring it to the dump, or you might give it away, or whatever, right? And in our companies, we do what we call, during the sort, we do what we call a red tag event, where you basically have an area, you do that exact same thing. What doesn't belong in the area, you put a red tag on it, move it into a red tag area, and then there's a certain amount of time where other people can go claim it. They can say, oh, we can use that desk, or we can go use that cabinet, or whatever is in that area. If after a certain amount of time, no one claims it, then it goes in the dumpster, or you get it out of the building. So again, in case of my garage, everything goes out on the driveway. Whatever doesn't belong in my garage, it's not going back in. Now, the second is straightening or set. All that means is if it's going back in my garage, it's going to have its own place. It's not going to just be randomly put somewhere. So there might be shelves, there might be labels. But everything that I have in the area has its own place. And the way I think about the set is, I don't know, I wish I get the sound worked, but in your kitchen, you have 2 drawers probably, right? I know I do. One drawer is where the spoons, knives, and forks are. And you open that up and they're all nice and lined up. They usually have a little set tool in there. And then there's another drawer with all the Tupperware stuff and the chef stuff, and you can't hardly open it up. You got to put your foot up on the counter to get it open. That's the opposite of set. One is set, one isn't. And then the shine part is make the place shine. So as long as I'm doing this, paint the floors, paint the walls, and I do this in my garage all the time. I have an epoxy floor in my garage, power wash the floor, wash down the walls, change the light bulbs, make it shine. And then the last 2 are the hardest ones. One is Saiketsu is standardized. And the way I think about standardized is checklist. Like if I wanted to involve my wife in 5S, I would ask her I'd come up with a checklist of how I want to keep the garage. And I'd ask her I give her a checklist and I ask her to audit it, which is the sustain part. So that's what Oxford is really in the process of doing right now. They're they have their checklists, they have their audits that happen constantly. They're taking that information and making improvements. Very difficult, 5S. Sounds easy for the garage, but when you're talking multiple shifts, when you're talking a couple 100 people or more, a little more difficult. But once you get those last 2 things right, the standardize and sustain, the checklist and the audits, watch out. You never have to do it again. I've done 5S 100 times in my place before I figured out this way of go after the standardize and sustain first, get the checklist done. It's not easy. So there they are. I'm not going to go through them. Here's some of the benefits. They say, well, everybody thinks of 5S as housekeeping. And really it's 2 things. It's really about visual control and standard work. That's what it's about. And when you start to see some of these kind of percentages of improvement, things like reduced changeovers. If you think about it, if everything is where it's supposed to be, I'm not spending so much time going to find things for my changeovers, right? Reduced defects. I'm cutting flow and distance, how much walking people are doing, the safety component to it. There's a whole bunch of benefits. And I think anybody that goes through Oxford right now, I think you start to see the results of Jim and, and the people that have been trying to drive this success program home. I wish you could talk, Jim.
I can.
So I'm going to skip through. I think I gave you my version of it all. The rest of the S's. So the visual factory, the concept there is I should be able to walk into any area and I know the status, right? I know if we're ahead, I know if we're behind. A lot of times it's boards that you'll see red and greens. But it's a way of when you walk out there, you don't really have to ask anybody. And Ulbrich Steel's on the call. I think I have 2 people there. And if you look at their wire division, they have these vision boards kind of things. They call them pre-actor boards. But all you gotta do is look at them. You know exactly what's running, what's coming up next, when the PMs are gonna happen, the whole 9 yards. So it's trying to make much more, your plant much more visual. And it kind of goes hand in hand with 5S, because we're talking about standard work and visual control here. And Kaizen, this is an interesting concept. Sounds easy. Everybody says, well, Kaizen, that means change is good. And as I explained to the Lean Beret at PTA on Tuesday, that the picture on the left, the Kai, is actually a human being with their back turned to you with a whip in each hand, thrashing their back with the whips. And the pictogram on the right is actually a altar with a ox on it for slaughter. So basically what Kaizen means is self-sacrifice for the good of all. That's what it means. Very difficult. Luckily in this class, I have probably two companies that do Kaizen as well or better than anybody can do it. It's very difficult to do. There's a lot of lean companies that have the walls painted beautiful, the floors are beautiful. There's circle around the coffee cup, it says coffee cup on the label, and that's where the coffee cup goes, but they can't do Kaizen. So as we always try to do Kaizen first, try to get that going. That's the hardest one, right? How do we get, we have a whole bunch of improvements that we can do. We have a whole bunch of employee suggestions. How do we make it happen? How do we, it's really hard because we're all busy. Everybody's running. Kaizen. So the idea when you hear the word Kaizen, people think of Kaizen events, where they're 4 days long, full time. You have 12 or 13 people on the team and they go after a particular area or particular problem. The issue I always had with those was I never had, we always have a to-do list afterward that we never get to because we really can't do Kaizen. So the idea behind A3 is instead of doing these big events, can we break them into smaller ones and do them all the time? And that's what worked for me. My company, Duraflex, 70 employees, we would do 1,200 A3s a year, somewhere around there. Albrecht's done over 1,000 a year, for a while. So it's basically taking this Kaizen event and making it where it's much more manageable. So Kanban, this is a tool that means, in Japanese, I guess it means signboard or signal. And largely when we talk about Kanban, I like to think about the grocery store, because that's where Taichi Ono and, and others, when they came to America to visit, they were just enthralled by how our supermarkets worked. And the idea there is anything that goes through the register, anything that goes out the door, that's what they replenish, right? If 100 cans of Campbell's soup goes out the door, clam chowder, that's what goes back on the shelf. Not 150, not 20, not 10. So it's replenishment based on consumption. It's a signal to do work, okay? And I think there's going to be some opportunities, coming up to practice Kanban. And it could be a card, it could be a ticket, it could be a light. It's some way for the next station to know to do some work. It's a way to link separated processes. It's a way to link them together. I need some. So if it's a signal or a card, it gets replenished. And Poke-Yoke means mistake proofing. I'm going to take you through some time-wise. I have a whole bunch of real life examples of mistake proofing I'm going to take you through. So I'm going to probably shift gears on this in a second. And there's contact method, constant number. Basically, it's mistake proofing. It's a way to make sure if you start doing 5Y and it always comes back to we need to go retrain somebody or the same mistakes happening, don't automatically go and blame the person. Maybe the process is there's a lot of potential for a mistake in it. And I'm going to kind of take you through a handful of real life examples in a minute. All right, so that's the end of the improve phase in terms of this PowerPoint. But I just want to let me just grab real quick the Poke-Yoke stuff. I think it'll make pretty good sense. Are we still together? Here's a few, just to kind of ring the bell here. I'm not gonna go through all 25 of them, but there's one. Basically, hotels lose millions of dollars because people turn on the TV, they turn on the lights, they turn on everything, and then they go to Disney World for the day, come back like 12 hours later. This mistake proofing tool is, I have to, in order for lights and the TV to work, I have to put my card key in a slot. Saves tens of thousands of dollars. So, and the mistake it's trying to make is people forgetting to turn everything off before they leave. How about microwave? What's a mistake proofing? Oh, you guys can't talk. I can't put my hand in there and close the door, right? I can't put, I have to close the door before it'll start. Same thing with my washing machine, because people, I guess, used to do that. Things like spell check. That's a pokey-okay. You know, helping you spell things. Garage doors and elevators. At one time, people get crushed in a garage door. Can't do that no more. Or they get their hand crushed in the elevator. These are all examples of mistake-proofing devices. I can't overflow the sink anymore. Used to remember in school years ago, you walk in, it'd be like a flood. Can't do that. As soon as I let go of the handle, the mower stops. Because people used to like let the mower run and go probably try to unlodge something underneath. And they end up in the emergency room. Can't do that. Cars have tons and tons of mistake proofing on them. And they're getting even more and more sophisticated. Lane changing. Blind spot detection. The little rumple skins on the side of the road, you know, start to doze off. They wake you up. My favorite mistake proofing thing of all, and if I ever met the person who invented this, I jump in their arms like I'm gonna do to Mike when I see him. And that's the bottom right picture, is that gas cap with a little attachment to it. Because years ago, they didn't have that little attachment. So people would fill their tank with gas and the gas cap would go on top of the car. And then 50% of the time you drive off with the thing on, it would end up on the highway somewhere. You could actually go to like stores like Kmart or whatever and buy gas caps. So that mistake proofing. And the other one I like is the fact that it's impossible for me to put diesel fuel into my gas car, but because they just changed the diameter. People used to do that. They need a motor job. Just the way things get plugged in, much simpler. When you bought a computer 20 years ago, it was a full day project getting it to run. A lot of calls to helpline. Your circuit breakers, light sensors, turning off water. I can't talk. Oh, I was going to ask you what's the mistake proofing in a filing cabinet? I can only open one drawer at a time now, right? Before, people would go to the emergency room because the whole thing would crush down on them. I think you get the idea. This one here on the left is people used to throw their trays away at McDonald's or Burger King or whatever. Now it's impossible. It doesn't fit anymore. All right, that's this is so awkward. I apologize. I can't hear you. But so I'll send you the recording, and I think you already have the math practice. There's no changes to it. So if you don't mind just go ahead and do the regression analysis on that blob that you got for my weight, okay? And we'll no class next week. You have 2 weeks to do the homework. And again, I apologize for the technical problems. Have a great weekend, people.